Hello everyone, my name is Moutsiana and this presentation is about the role of ionospheric oxygen ions in ring current dynamics. The terrestrial ring current is located at an equatorial distance between 2 and 7 Earth radii. Its main carriers are various species of energetic ions in the energy range of about 1 keV to hundreds keV. The quiet time ring current is carried mainly by protons of predominantly solar wind origin, while it is also confirmed that singly charged oxygen ions originating from the Earth's ionosphere contribute significantly during active times. This compositional change can affect several dynamic processes, and therefore it is quite interesting to study. In our study, we used data from Kyoto for the indices DST, CMH, and AL, as well as data from the Orbispice instrument on board the Van Allen Probes B regarding ion fluxes in the available energy ranges. Our study covers the entire year 2015 and focuses on investigating proton and ion injection events. We note that the energy range of non-contaminated data is shown in the yellow box, which means that only higher energy oxygen ions are actually taken into consideration. Here we present the integral fluxes for protons and oxygen ions respectively across their whole energy range as covered by the Orbispice instrument. We notice a quite close correlation of the DST index with enhanced fluxes of both protons and oxygen ions, which is observed during events of various intensities. We also see that oxygen ions decay faster than protons, which is compatible with the charge exchange processes for the energy range covered here. These are plots of the oxygen ion over hydrogen ion integral flux ratio as calculated for the common energy range of the two ion species and based on an omnidirectional flux that follows a power law distribution. Enhancements of the flux ratio correspond to oxygen injection events in the inner magnetosphere, and we can see clearly that such events correlate well with geomagnetic activity. We can also see that more intense storms are associated with enhancements of the ratio in lower L shells. If we zoom to June, we can see that during storm main phase, the ratio increases greatly, which means that the flux of oxygen ions in the ring current increases faster than the flux of protons, while during storm recovery phase, the ratio decreases, meaning that oxygen ion fluxes decrease much faster than the proton fluxes, which is again in consistency with charge exchange process in the studied energy range. If we focus on some special periods of time, we can see that there are cases where enhanced ratio values are observed, but they're not accompanied by storm occurrence. In such cases, substorms are responsible for the increased values, which are, however, confined in higher L shells. When substorms occur during magnetic storms, both phenomena seem to contribute in the further enhancement of oxygen ions in the inner magnetosphere and the displacement of ejections in lower L shells. We also calculate mean values of the oxygen over hydrogen flux ratio for the three L beams noted here, and we demonstrate the results during June for better resolution purposes. The colored points represent flux ratio values calculated for the common energy range of both ion species. The difference of the black points is that we take into further consideration oxygen ions of higher energies. Due to the proximity of the colored and black point values in all L beams, which is observed for the entire year, we conclude that the oxygen ions with energies greater than 600 keV play a minor role in the decay rate of the ring current. Assuming that the oxygen ion flux follows the exponential decay function shown here, in such diagrams, slopes correspond to ion decay rates. We see that for different storm intensities, different slopes are observed, which correspond to different decay rates, indicating that oxygen ions loss processes depend on geomagnetic activity. This actually suggests that in addition to charge exchange, other loss processes such as Coulomb decay and pitch angle scattering may also play important roles in oxygen loss during storm recovery phase. Thank you very much for your attention.